So how to evaluate the volume of the sphere radius 1, not by approximation, but the exact value. I'm not going to go all the way through because, well, as you see in a moment. But the point is that just, where we are right now is Fubini's theorem, which is about converting double integrals into iterated integrals. So we discovered we did it with rectangles, and similarly in dimension 3 you would do boxes. Very easy. You just have two integrals with limits. We have 3. The difference is really negligible. Where is it? That's not it. Still no. Here it is. So this is Fubini's theorem for dimension 1, dimension 2, double integral, and we convert to, we have the limits of x and y, because it is a square, they are independent of each other. Okay, so x, there are limits for x, there are limits for y. It is literally, our rectangle is the product over there, you see, of those two rectangles. Okay, so and that's why things work out so easily. Once again, that's I did example possibly somewhere when you are integrating a function of 3 variables over a box. Okay, so very similar situation, very similar formula, except you'll have 3 integrals over there. Okay, so there is no challenge whatsoever, and you just the complexity all comes from the function. So you have to carefully ignore the 2 other variables, think of them as parameters, and then go through integration. We'll do that example again, but it is really in comparison to what we're trying to accomplish now is kind of easy. So because that's where like I said, the challenge and the complexity is with the function. And now the actual complexity is not with the function, but rather with the origin. Setting up those limits frequently is the main challenge. So we did solve that problem here. And then we know what this discussion that came from areas, matching areas in calculus 1, areas that we derive from integration or double integration, which the area is, that is the, pretty much you can think of this as the definition of the area of a region on the plane. It is a double integral of a function equal to 1 over that region. Okay, so then these two have to match. Okay, if we happen to have the region that's like a region under the graph of a function of 1 variable, then computing the double integral of that region should produce the same result, and it does. So once we set that up, we are then looking at integral with double integral, but with the limits, as you can see over here, the limits with respect to y being variable. Okay, and they are variable. Look at it as we're moving from right to left, from left to right. So we're moving, and then the height of the graph as we move along it changes. So this is one value of x, and that's the next value of x. Okay, and it has changed. Okay, so and these are the values of y. So we cannot think about this region. Once again, that's certainly a source of confusion. Is the picture on the left, picture on the right. We may be talking about the same thing, but now we're not doing single integrals anymore, but doing double integrals, and then the area, the region rather, like this, is not what we're looking for. We're not looking for its area typically, but rather we are thinking of this region as the region of integration. Okay, so it has to be set up properly in this fashion that is over here in order to be able to use these for well, functions in a way as limits of integration, and so as you can see, it is confirmed that we could do Fubini's theorem. This is Fubini's theorem over here to match the result from calculus 1 and the result of double integration. Okay, so as you can see, double integral of a function of 1 over that region over there is equal to simply the usual integration from a to b f I dx. Okay, so so that is just the idea of where it comes from, and the like I said, the hard part is right here. how to find the representation. This one was fairly straightforward, but it pretty much captures everything that can possibly happen. So, and this one is the same story. So you forget about the function, which is really not necessarily the more complicated part, but rather setting up the limits is. So once again, remember what I did. I chose the limits for x first. It's up to you whether you choose x first and then y, or y first then x, then x. That doesn't matter usually, even though frequently one of them is simpler than the other. In this particular case, x and y are symmetric. So the sphere itself is x squared plus y squared plus z squared is equal to 1. And that what gave me the function. But on the other hand, in addition to that, that formula also gave me this. That same exact formula gives me what? It gives me the intersection of my sphere, or half sphere, with the xy plane. So this is xy, z, and now I just set z equal to, in that formula, z equal to 0, and I have my equation x squared plus y squared is equal to 1, and that's a circle on the xy plane, and this is the domain of integration. Just to, it is not enough to do this. It is no more than just a notation. So this is just notation. We cannot use it for computation with just a few exceptions. And so we have to do this. So we have to convert with Fubini's theorem this double integral into two iterated integral to have any chance of solving the problem. So, but we still have to identify the domain integration specifically. So I did over here. So that is the region. So that the whole solid, the half of the sphere, lies above this region. Okay, and it does not only does not stick out, but also there is no. Well, it's literally it is a not just I said intersection, which it is. But it is better in general think about projection or shadow of our solid on the xy plane. That's what region of integration is. So you have some kind of complex body that you want to compute, maybe like this. Then what's the region of integration? This is, or region or domain of integration. That's what it is. Okay, so then once you set up the integral, which we are about to do, then we'll see if it is feasible to compute it. But that's the first step. It has to be carried out. So once again, x between -1 and 1 on the x-axis. So we choose x to be the independent variable in this relationship, and then as we're moving through the domain for x, the value of y varies. The range of values of y varies, and these are its limits. So it's either from here to there. Okay, so this might look familiar. Does this look familiar from calculus 2? A little bit. It is just the same thing in a way, just slightly more general. We'll discuss that in a minute. Let me set up the integral. So Fubini's theorem. So it will be the integral from dx. So from it will be the second. The last integration will be with respect to x, and it will be between -1 and 1. In the meantime, here inside is the integral with respect to y, which gives me what? It gives me this. It gives me the area. So see, this is the hold on a second. Hold on a second. So x is fixed. Yeah, x is fixed. Okay, yeah, x is fixed. So if we are, we set up this for x, which means the x run between -1 and 1. So suppose now inside the parentheses x is fixed. So that's a fixed x. A fixed x gives me an edge for y's of a variable width, which is given over there, and that will be my integral. So it will be literally integral between -1 minus x squared to 1 plus x squared. 1 squared of 1 minus x squared. Okay, the function is naturally the same. 1 minus x squared minus y squared dy. Okay, so the question that I was asking is, let me mark this. I started to ask, so these are the limits which we are already marked over there. What's the meaning of the integral inside the parentheses? Geometric meaning. Can you point it out on the picture?
Just the area of the circle?
No. No, let's see. No. Think about, so it's happening along the y-axis, but not on the y-axis. This is where it's happening. So this integral is for a fixed value of x, so it's not here, it's over here, because x is fixed, but it's not necessarily 0. So that's our edge, which is the domain of integration of this function of one variable. This is a function of one variable because x is fixed. Okay, so we can see it over there. So what's the the function then is this. Okay, the function is this function when x is fixed turns into that curve over there. This one. So it's the same function as the circle formula at the top, but with I missed the square over there. With x fixed. Okay, I see. Well, my problem. I messed it up. Okay, so because you know why, but I'm doing it along the y. I'm crossing the x-axis, so well that might explain a lot of confusion here. I'm cutting along the y-axis. I'm cutting the x-axis along the y-axis. So let me try to do it again. Okay, so as you can see, so as you take this picture and the x-axis is pointing at us. So I'm crossing that purple edge is here. Okay, and then we're cutting with that is a fixed value of x over here. So here x fixed over here. Okay, so once x is fixed, we are then throw out everything else from the whole thing, and so we're cutting our sphere with the vertical plane. X fixed is a vertical plane like this. Okay, and so I end up with it is a half circle, but the radius isn't 1. Okay, so this is our function. So it's given by the same formula, but x is fixed, and it is a function of one variable, being y. Okay, so as you can see, this picture clearly shows that the y varies. Y x is fixed. And so we're computing, then this integral in parentheses is the area, well, in green, of the area of a cross section. Okay, so these, as to integrate, you do it one variable at a time. You fix that you fix the other variable, so you fix x while still allow y to vary, which means that you are crossing, as we have in the past, your surface with a vertical plane, which produces a curve. So you have a plane with a curve on it. So like I could probably do even more here, like this. So this is my plane with x fixed. With x fixed, I have a plane, and then everything. If I stick to these parentheses? Everything is happening within that plane. Okay, and so every integral then like this is for each x will give you the area of that cross section, which varies. Okay, so once again, if you think about it, so what we are integrating is the areas of the cross sections. That definitely should sound familiar. Integrating areas of cross sections to find the volume Anybody remembers what this is called? So calculus 2, remember, do you remember computing any areas? Sorry, any volumes in calculus 2? Any volumes in calculus 2?
The toilet paper roll.
What?
The toilet paper roll.
Paper roll. I'm not sure what you're referring to. What is it?
Like a roll of toilet paper has a hole in the middle.
Okay.
The area of that.
No, the volume.
Yeah, the volume. Yeah.
The volume of okay. Okay. So
Is it called volume of revolutions?
right. So in other words, what?
Was it called volume of revolutions?
Well, volume of revolution would be one, and so I think that what you might be referring to is pretty much what certainly worth knowing is the volume of a cylinder, right? So you can't really use anything else to find the volume of a cylinder, but some kind of a double integration, right? So that one would be fairly easy to compute, but what I was referring to there's a name for it. It's called the Cavalieri principle. Cavalieri. So it says exactly that. It doesn't have to be named this way, but because it goes so far back into oh, I'm not sure how long, but probably possibly contemporary of Newton's. So before the modern mathematics, it is what I have here is the volume is equal to the integral of the cross section. So you keep crossing, you create a function of x. For each x, you have the area, you compute that area, and then you integrate those areas. It will give you the volume. So that's what Cavalieri principle is. And Fubini's theorem is very similar, it is closely related. The only difference is we sort of take it one more step in the computational direction so that we can also know what to do, how we find that areas. How do we find that area that is part of the Cavalieri principle? We find it by another integration. So instead of having one integration of some area, which is unknown how to find it, we have two consecutive integrations. That's the difference between the Cavalieri principle and Fubini's Fubini's theorem. Incidentally, since it came up, you can tell from the Cavalieri principle what is the volume of the cylinder of radius r. Well, I mean, you probably, in case you don't remember the answer, it's very easy to recover it from this, from the Cavalieri principle. So radius, cylinder, radius r, height h. Okay, so this is h, and the radius is r. So, okay, it's just like a snap computation. What are the cross sections?
Pi r squared.
Pi r squared, right? So it is independent of x. So if you put your x-axis here, then it is the same. So this is the area of the cross section. So what do we do next?
Integrate it from 0 to h.
0 to h. What's the variable?
dx.
dx, that's right. It's not dr. R is fixed anyway, and so x. And so in other words, we integrating a function that happens to be constant. So the answer is then constant function. How do we integrate constant function of one variable? That's just regular numerical integral.
It's just pi r squared to x.
Pi r squared h. Yeah. So that's it. Okay. So that's kind of how from the Cavalieri principle you get that formula very easily because the cross section is exactly the same. Incidentally, if you try to cut it, the choice is yours. So if you try to cut it like this, you are in order of pain because the cross section will vary in areas. So it starts with 0 So same cylinder, but you're cutting it along the axis rather than across the axis. So starting with 0 area, then it goes all the way to every time you have a rectangle. So that's still doable, and that may have been one of the examples that you saw in Calculus 2, is computing something like that. It could be either a cylinder being crossed, and or how about a cone, another one, another good example, when you start cutting it like this, and then each of them is a circle, but the radius varies depending on x. So these are shortcuts of how to compute values without invoking double integrals. So there are no double integrals in Calculus 2, and but there are shortcuts which actually go way back, and that's based on the Cavalier principle. You can compute quite a lot of things, but they are mostly like surface of revolution, or well, these are all, well, it doesn't have to be surface of revolution, these two are, but you can also have, say, what is the word of it for it? I don't remember. It doesn't matter what the word is, what the cross section is a triangle. Same idea, so as you keep crossing, the triangles get smaller and smaller, so the computation is pretty much the same, but there is something to integrate. Okay, and this is not a surface of revolution. Okay, it's also computable from the Cavalier principle. But it is entirely, first of all, it skips the idea of double integral to begin with, and the meaning of the volume as a double integral, or, well, if we want to be honest, the volume is a triple integral, not a double integral. And so, as we've already established, I hope, is that the area is not a single integral, it's a double integral. Right? That discussion over here should put rest to that idea that the area is a single integral. It is a double integral, because as you can see, the treatment of areas in Calculus 1 is limited to graphs and areas under the graphs. In Calculus 3, we can handle almost every shape or form by choosing of origin in plane, by choosing that region that we're interested in. We choose it not to be like this, but rather choosing it to be the domain of integration. Okay, so as long as you can integrate a function so simple as 1 over that region, you can compute its area. Okay, so once again, areas are double integrals, and the volumes are triple integrals in the same manner, as we will see shortly. But at this time, still avoiding the idea that you probably compute volumes by double or triple integration, firstly, and which is not surprising really. I mean, how do you compute the volume of a box? You multiply 3 times those 3 dimensions. So 3 items being multiplied, and it's the same thing. That's what integral is. And then secondly, it also avoids the question of how to find that area. So Fubini's theorem will help us with that. In the meantime, so there's really no work to be done. We have set up the integral. So the work here is pretty much Calculus 2. So how to integrate any particular function? You do it one at a time. So each of these 2 integrals will be simply the integral of one variable. Okay, so doesn't mean that it is easy, but at least it is. The problem has been reduced from double to single. Okay, so the formula, since I copied it right here, so in case you don't remember, I certainly don't. But the formula is familiar, or maybe anybody remembers how to integrate that function that circled there in green, square root.
Or it's a trig substitution.
It is some kind of a trig substitution, yes. Certainly, yeah, that's right. Well, because it is. It is. You just have to be careful about what is your. Be careful about that your variable is y, which means that 1 minus x squared is what it is. I have to stand against. So usually it is 1 minus y squared. Okay, and now 1 is replaced with 1 minus x squared. So there's some dependence. So let me just try to write it out right here. What the answer might look like, not the final answer, but is the integration. So it's gonna be y over 2. It will be a mess. 1 minus x squared minus y squared, okay, plus 1 minus x squared over 2 arc sine y over 1 minus x squared, okay, from, and with those two limits, 1 minus x squared, 1 minus x squared, and then the x. Okay, so, yeah, that's it. So I do expect simplification because we know the answer is we already know what the answer is. So once you start plugging things in, you can see, well, let's spend a second and see if things do simplify. I just didn't take it all the way through, but you can see if now y is replaced with those expressions. So these are, once again, it helps often to, when you have two independent variables to integrate or differentiate with respect to, then writing those variables is very convenient. So you know where these go. So these two are being substituted into this long expression, and so what's going to happen is it appears that this will disappear, doesn't it? The square root in the first one will disappear. If y squared is equal to 1 minus x squared, this term will disappear. In the meantime, arc sine of -1, this will be 1, or this will be plus or minus 1, right? So arc sine of 1 is pi over 2. In other words, it will be pi. Maybe I'm doing it too fast, but so does it look reasonable? So if now I start integrating, I'm going to have 1/2 x minus x cubed over 3 from -1 to 1. So it's going to be, it does look reasonable actually. Okay, so if I plug in 1 minus 1/3, 2/3, plus 2/3, so it's 4/3, 2/3. I lost my pi here. Where's my pi? Yeah, it worked out. It worked out because it's half of the sphere. Remember, the answer 4/3 pi squared is r cubed. I'm sorry, the volume of the sphere. So quite a scary looking integral over here, but actually it is not as scary as an indefinite integral. As a definite integral, as it often happens, things simplify. But then again, the whole problem was designed in such a way that it would work out. So I mean, it was solved so long time ago that there's nothing that can go wrong here. So as long as you know, I picked the one from the back of the book, that formula, and in black over there. And then you certainly feel free to do that when necessary. Even though there's a point to it, it's like there are certain things that they present the most challenge in calculus 1, 2, and 3. So what was the main challenge in calculus 1? Anybody remembers? Well, to me it appears that the main challenge is usually differentiation whenever the chain rule is involved. So because if in calculus 1 you don't quite understand compositions yet, then you have big trouble, and it happens too often. We're going to face it again, except functions are more complicated, and we'll have to deal with the chain rule when we have all kinds of compositions of various functions of multiple variables. And then, so it's a computational problem that creates problems, unfortunately, and because it's such a big problem, it might appear that it is what calculus is about. And the same problem in calculus 2, which is what is the main challenge, is usually integration. Integration by substitution, and you look at the formula, you have to say, well, we integrate by parts first, and then you do trigonometric substitution, something like that. So that's a challenge to recognize what's supposed to happen and then carry it out. And once again, because it's so hard that it might give you impression that that's what calculus is about. And then we are right where at the spot where it is frequently the biggest problem in calculus 3 solving problems like this. Not this part, but rather this part. How to represent some three-dimensional solid in these terms, so you can do Fubini theorem. Okay, so problem would be, for example, as one I saw just not too long ago. So suppose you have a bucket that, we'll say, 1 meter by 1 meter, and then you fill it with water, and then what if you tilt it? You tilt it, and then you fill it with water, and then you tilt it, and the water spills, and the question is how much water do we have left? I'm not sure if I do it correctly. So like this. Okay, so that would be a question, kind of killer question to solve a problem like this. So the volume. Okay, so it's almost spilling. Almost spilling. Certainly we know the volume of the cylinder, but that doesn't help us at all, because look at the how complex it is. It is a piece of the cylinder that we're supposed to compute the volume of, and what does it look like? So it is an ellipse. Okay, so it has a horizontal ellipse right here. It has a piece of the cylinder here, still, it didn't go away, and then there is the circular part too. So it's well, I don't know what it looks like, frankly, hard to describe. So once again, the top is that surface of water, which is flat, horizontal, and then you have this one tilted at whatever the angle is, and then this one also not quite clear what the angle is. And so you're supposed to find the volume. So it's a challenge, but it is a computational challenge rather than like a conceptual challenge. So you would have to go ahead and represent this one as in the way of Fubini theorem. So this one probably will require 3 variables rather than just 2. So, well, like I said, it's a challenge. But I think the projects that kind of that you have faced are actually more interesting and more profound ultimately than the computational problems of this nature. Okay, so the volume of a solid is the integral of its cross sections, and the integral. Well, let me write it up again. So the volume, Collier principle, volume of a solid between, say, z equal p and z equal q. So between 2 planes, okay, is equal to the integral of the area of the cross section from P to Q. So in other words, the volume is equal to integral from P to Q a z dz. So it was ax dx naturally in calculus 2. Dealing with one variable, but now we know that we are going to be figuring out this area. It is better when this area, this cross section, is horizontal, so that it is in the xy plane. So that way we can look at this and ask ourselves what kind of areas we can handle without invoking double integrals. Okay, so you don't want to make a full circle, even though I made a big point of that the areas are actually double integrals. But since we are trying to compute a double integral to begin with, then you don't want to use double integral to compute the area, which is also double integral. Okay, so in other words, computed by means of calculus or pretty much calculus 1. Okay, so it means that only some of the regions can be handled. Specifically, the ones that lie between two graphs of functions. So y equal, say, g1 of x, and y equal g2 of x. Okay? So a, b, x, and y. So our solid certainly lies in the three-dimensional space, but then we are looking at either shadow or its footprint, and it better look like this, because now we know how what the areas look like, and they look, they're the ones that we can handle with the tools of calculus 1, and these are the only ones that we can handle. So once again, we are cutting, hold on a second, so we're cutting horizontally, right, and each region should look like this. Each cut should look like this. If that is the case, then we can have the answer. Okay, so that is just let's just say we stop here and not try to go further, because I think it's easy just to go straight to Fubini's theorem and state it without relying on the Cavalier principle. I think we see the connection. It just has to be done carefully. The actual formula is uncomplicated. It just has to be written appropriately. So, okay. Okay, so we are, so we're talking about the other difference is that with Fubini's theorem we usually integrate something. So Fubini's theorem, and so f is integrable over some region R in the plane. Okay, which is to be specified, and we want to compute this integral f double integral over R dA. Okay, so and then it is equal to the integral what we already saw in that example. So it will have two consecutive integrations with respect to the variables that you pick, so I'm referring you to the example of the sphere, half sphere. Okay, and then as you can see, only to be determined are these limits. Okay, so say this is AB, the picture already we just saw, and here we have G1x, G2x. Let me write y here, so there would be no doubt what we're talking about here. So once again, inside the parentheses, everything x is fixed, and we are integrating with respect to y. Okay, and we are looking for the cross section of that region of the region under. This is still a region under the volume under. It doesn't have to be, but it is the volume under z equal f of xy. Okay, so so where? So it has to be explained where these came from. Where R is the region on xy plane, and this is how carefully we write it down with a point xy, pairs of xy, not separate condition on x and y, but separate x, we chose to be the independent variable, and it is equal to, and it is allowed on an interval. Any number is allowed, but y is limit is squeezed between two functions of x, as that picture I just showed you. This picture. Okay, that you saw either later in calculus 1 or early in calculus 2, finding areas between two graphs, right? So we are not looking for that area. In a way it's there, but it is what we're talking about here. Let me still make that three-dimensional picture here. So y and x and z. So what does the region look like? X between a and b over here, a and b, and then there are two functions. y equal g1 of x, the smaller one, and y equal g2 of x. So careful with the powers, certainly, with the order of the two functions. So if they start one below the other, there might be trouble. Okay, so then we cut it like this, which creates my origin right here. So that is my domain of integration. And then, of course, there is the function f somewhere. It's still here. So we are just to make the picture complete. I'll put it right above. There is some kind of a surface, which we are trying to. What does it do? It simply bounds the solid here. The solid under this region. So we are out of the sandbox already, because as you can see, the domain of integration is curved, which means that we still have a vertical walls, but at least the base of the region is not rectangular. Okay, so